on prime permutation count solution. So let's just see what is the given problem. You are given an array A of size n containing all the unique numbers. So you will be given an array of all integers of size n with all the numbers unique. There will be no repetition. Your task is to find the count of permutations that can be formed from all the subsets of array A. Your task is to calculate all the subsets of the given array A and calculate their permutations, but the subset should be strictly containing only prime numbers. So all in all, your task is to filter out all the elements which are prime, calculate the subsets of them, and then calculate the total possible permutations for the given subsets. This count can be really huge, so you need to find the count modulo 10 raised to the power 9 plus 7. So let's just see how we can solve the problem. So let's say that the given example is 2, 3, 5, 9. From these given elements, 2, 3 and 5 are the prime numbers, so I can filter them out separately. Then all the subsets of these three elements are going to be 2, 3, 5. There will be 3 one length subsets. Then 2, 3, 2, 5, 3, 5. There will be 3 two length subsets. And then 2, 3, 5. There will be 1 3 length subset. The total possible permutation for the one length subset is going to be 1 each. So 1 each coming from here. So there will be total 3 permutations here. Total permutations of 2 length subset is going to be 2 each. So 2, 2, 2, total 6 coming from here. And total permutation for 3 length is going to be 6. So 6 again coming from here. So 6 plus 6, 12 plus 3, 15. So 15 is our answer. The length of the given array can be as big as 10 raised to the power 3, and each element can be as big as 10 raised to the power 6. So let's just see what is the brute force solution for the given problem. The brute force solution says that we can generate all possible subsets containing only prime numbers and then calculate their permutations. But the first question that arises is how to filter out all the prime numbers. So let's say if the given array was 2, 3, 5, 9. From this array, we need to filter out 2, 3, 5 because these are the only prime numbers, right? How can we do that? So this is a fairly simple logic, and I hope all of you guys already know about it. That is, you can go at every position, at each element you can go, right? And then you can check whether the number is prime or not. How to check whether the number is prime or not? A prime number is a number which gets only divided by itself and 1. So there will be no other divisors for the prime number, and or we can say there will be no other factors. So, and we know that for any number a, the unique factors for a resides in the range 1 to square root of a. So what we can do is we can go from 1 to square root of a, and 1 will always divide it, so there is no point of taking 1. We can directly take 2 to square root of a, and then if any of the number in this range divides a, then the number a is composite, otherwise it is prime. This logic will work in order of square root of a into n time, right? Because for each element you have to do this logic, and for one particular element it will go till square root of a. Now what will be the number of operations here? N can be as big as 10 raised to the power 3. Square root of a will be also 10 raised to the power 3. 10 raised to the power 3 into 10 raised to the power 3. This will be 10 raised to the power 6. So filtering out the prime numbers is a fairly easy task for us. But the main issue with this brute force solution is that if we will try to generate all possible subsets, then this filtered array of primes, let's say, is of length m. This can be as big as n only, which is as big as 10 raised to the power 3. Let's consider a case where all the given numbers are already prime. Then in that case, the total possible subsets is going to be 2 raised to the power m minus 1. This is the count of all the non-empty subsets, which will be 2 raised to the power 10 raised to the power 3 minus 1, which is a really huge quantity, and this solution is going to give us TLE. Right, we are not going to be able to submit this solution because this exceeds the 10 raised to the power 8 operations limit. So how can we optimize? One thing that we can definitely say for sure is that using this square root mechanism, we can filter out this array and get all the prime numbers. This is something in our permissible limit, so we will use it. But how to generate all the possible subsets and then calculate the permutations? This is something that we can optimize. So technically you can see here, we just need the count. We don't need to actually see the subsets. So can we do something so that we don't have to actually generate the subsets and somehow we can get the count? Let's just see. So here you can see that there will be some subsets. If let's say the prime number array looks like P1, P2, so on and so forth, Pm. This is of length m. So some subsets will be of length 1, some subsets will be of length 2, some will be of length 3, some will be of length I, and then some will be of length m. Right? Now, any one length subset will be permuted in 1 factorial ways. 2 length subset will be permuted in 2 factorial ways. 3 length subset, because all the numbers are unique, right? If there is an array of 3 elements, the total possible permutation is 3 factorial if all the numbers are unique. Similarly, an I length subset will be I factorial ways permuted, and m length will be m factorial ways permuted. So this is the number of permutation for each subset that we will get for any length I. Now, how can we get any I length subset? So, for subset, what we know is all the numbers are unique. So, in order to find a subset of length I, what we need to do? We need to find any I numbers from the given m numbers. So, in how many ways you can choose any I numbers from the m unique numbers? The total number of ways is going to be mci, where c denotes the combination, which is equals to m factorial by I factorial m minus I factorial. This is the value of MCI. This denotes the number of ways in which you can choose any I elements from the given M elements. Right? And if you are able to find that how many ways you can choose the I elements, this is equal to the total number of subsets of length I. And one subset of length I is permuted in I factorial ways. So these total number of subsets is going to be permuted in MCI into I factorial ways. Can I say that? And if you multiply this quantity with I factorial, this I factorial value gets cut out. This is going to be equal to M factorial by M minus I factorial. So this is the quantity which denotes that in how many ways how many permutations of all the I length subsets are there. So what we need to do, we need to find the count of all such permutations. So what we can do is, we can just simply sum them up. So it will be equal to summation of m factorial by m minus I factorial, starting from I is equals to 1 to m, and we can do this summation whole modulo 10 raised to the power 9 plus 7, right? So what is this quantity denoting? We know that m factorial by m minus I factorial is equal to the number of permutations of all the I length subsets. We have to calculate all the permutations. So all the permutation of 1 length subset plus all the permutation of 2 length subset plus all the permutation of 3 length subset, so on and so forth. That's why we are doing summation. And then this whole summation will go in 10 raised to the power 9 plus 7 modulo. Now how can we calculate this value efficiently? So you can see that this is a factorial quantity. M factorial and m minus I factorial is a factorialish quantity. So what we can do is, we can pre-compute factorials. Right, we can store an array where any jth index is going to store j factorial, because we know that any value j factorial is going to be what? J into j minus 1 factorial. So we can store j minus 1 factorial already, and using j minus 1 factorial we can compute j factorial in order of 1 time. Then using j factorial we can compute j plus 1 factorial in order of 1 time, so on and so forth. So if you have factorials computed already, then m factorial by m minus I factorial can be calculated in order of 1 time, and you have to do this order of 1 task m times. So this can be solved in order of m, which is as big as n in the worst case. And this factorial, how many factorial you will require in the worst case? In the worst case you need to calculate m factorial. M can be as big as n, so you need to calculate at max n factorial, that is order of n only, right? So using this order of n loop, you can compute this pre-compute this factorials, and then as soon as you have the factorial, you can just divide them with the corresponding value of m and do this over a loop starting from 1 to m. And this factorial and this summation, both of them will be working with respect to modulo 10 raised to the power 9 plus 7. If you don't know the modulo arithmetic rules, I have already written it for you. A plus b mod c is a mod c plus b mod c whole mod c, and a into b mod c is a mod c into b mod c whole mod c. Why these formulas are there? Because let's say a is a very big quantity, b is also a very big quantity, then their product can be a very huge quantity, and that can overflow the limit of the given range. So what we do, we first reduce a to the range c, then b to the range c, and then their product is then again reduced to the range c, because any value m mod c is going to lie in the range 0 to c minus 1. So this modulo value is going to be definitely lesser than a and even less than c, because it can have a maximum value c minus 1. So using these formulas, you can calculate a plus b mod c and a into b mod c, which is going to be used in this summation and this product. So let me show you the final solution to this question. So here you can see that I have prepared an array factorial which is going to pre-compute factorial. This function is going to help us pre-compute the factorial. Here I am going from 1 to 10 raised power 5. You can even go to 10 raised power 3 because we are just doing pre-computation. And any ith factorial, if you already have the value of I minus 1 factorial, we can just multiply I with it and we can get I factorial. And you can see this multiplication is comprising of modular arithmetic. Then we have this is prime function which is starting from 2 going till square root of none and checking if any number inside this range divides the given number. It is definitely not prime, that means returning false. Otherwise, if the number is greater than 1 and was not able to divide itself with any of the numbers in the given range, it's a prime. Then in the final count permutation function, we are first pre-computing the factorial array. Then this PR is actually denoting the count of primes, which is eventually our m. Then what we are going to do, we are going to go to all the numbers one by one and check which of them is a prime. Whenever we find a prime number, we'll increment the count. This is eventually our value of m only. And then at finally what we are going to do, we are going from 1 to PR, that is 1 to m, and then just summing up PR factorial by PR minus I factorial, which is equal to m factorial by m minus I factorial. And again this operation we are doing with respect to modular arithmetic only. So I hope that you guys enjoyed this solution and you are able to understand this whole solution completely. Try to implement this solution once on your own as well. This will help us you to get more confidence on the problem, and we will meet on the next video. Till then, take care guys. Bye bye. Have a great week ahead and